Is Professor Valeria Cavalcanti from the State University of Maringá. She will talk us about exponential decay for a nonlinear Corte-Vedebris-Burgers equation with indefinite damping.
First of all, I would like to thank Professors Felipe and Hermano for the kind invitation, and it's an honor to be introduced by Professor Perla Menzaba. This is a work in progress, and it's a joint work with Professor Marcelo Cavalcanti and Vilmos Komornik, and my student José Henrique Rodrigues. Okay, it's in fact it's a part of a work we are done. And my talk will be divided in 3 parts. So I will introduce the problem. I'm going to show the global existence of the KdV-Burgers equation, and then I will show you the exponential decay result. And the goal of this talk, and I will divide the 3 parts, but the goal of this talk is the last one. The goal is to prove the exponential stability of this following Cauchy problem, where this function lambda, okay, is essentially bounded, and each is allowed to change sign. So this is a damping term, but it can change sign. So, okay, and each will be the term which will give us the exponential stability of this problem. And we are motivated to study this problem by this equation, and this equation arises in modeling the propagation of planar waves when somebody wishes to observe interaction of nonlinearity, dispersion, and dissipation phenomena. And this equation is referred as KdV-Burgers equation because it's the union of the KdV equation and the Burgers equation. Okay? The solutions of this equation, this one, the KdV-Burgers equation, approach to 0 when t goes to infinity. And you can ask me how it goes to 0. So, in this work of, in this work of Amick, Bona, and Schoenbeck, they showed the following. They proved that the corresponding solutions to that problem, when the initial data belongs to this space, verifies direitos for all t and for a positive constant, and they prove also that this estimate is optimal when they have that this integral is not 0. And we kept thinking, but if we add something in that equation, something is a damping term, perhaps we can have exponential stability. Okay. If we consider the linear KdV-Burgers equation, this one, it does not satisfy plus condition, so it never decays exponentially. So we are not in the right direction. We have to add something in order to obtain exponential decay. So if you add a damping term where this lambda has a lower bound, which is positive, we have this result. Okay, it's exponentially stable. But when this lambda can change sign, it's not natural to think that if you have or not exponential decay. That's what I'm going to prove to you. Okay? So that's the goal of our work. So we are going to prove that if this this function lambda has not a positive lower bound and can possibly be negative. So, to begin with, we are going to prove the global existence of solutions. So, in order to obtain the global existence of solutions to our problem, we consider this operator A defined in his domain and considering the values in L2. And this operator is a generator of a strongly continuous semigroup of contractions. And so if you have initial data in this space, we say that it's, U is a Miles solution of our problem if the integral equation is verified for at almost for every t in the half plane. Okay, and here S will denote the semigroup generated by A. If you want to set in a more generous situation, we are going to give capital T greater than 0, U0 belonging to L2, and F in this set here. Using semigroup theory, we are going to consider this linear inhomogeneous initial value problem associated with our problem, our initial problem, the KdV-Burgers equation with the damping term lambda U. It admits a unique mute solution in this class given by this formula, which depends continuously on the data. That is, its solution verifies this inequality. In fact, in order to prove the global positiveness, we are going to prove two propositions and then the theorem. In fact, we have this result here. If we have U0 belonging to L2 and F in this subset, the solution U of this problem here, 8, that I'm going to call 8, its solution belongs to no more in L2 but here in H1, and in addition we have the energy identity holding for every T belonging to this interval. So how we prove this proposition? We consider smoother data, and then we get a smooth solution related to this smooth data, and then we get this expression here for this smoother data, smoother solution. Then we do some computations and we use Gronow's lemma and we get, and then we get this expression here. As our problem is a linear one, we get this. And so we conclude that our sequences are Cauchy's ones, and then we get a limit of the sequence, and the limit of the sequence is the solution of our problem related to the data U0 and F, and the energy identity is derived from our identity with N. The other result is the following. If we have U in this space, then these terms belong to this space, and then this application is local Lipschitz from this space into this space. Okay. If you consider, if we consider this embedding, we have this, of course, for almost every T. And in addition, we have this inequality, and then we get this expression here. If we consider U and V in this space, doing some computations, we get this expression, and which proves that this application is a locally Lipschitz one. So, inspired by this proposition, we define this space B which is a Banach space if we endow this with this norm for every u belonging to B. So if we consider u belonging to B, a solution of our problem 8 related to some initial data u0 belonging to L2 and f belonging to this space, then the energy identity implies the following estimate for this u belonging to B. Okay? Now we are going to establish the global existent result using a fixed point argument based on Rosier and Pazot's ideas that constant in this paper here. We are going to consider initially the lambda being an essentially bounded function, and given u0 belonging to L2, there exists a unique solution u in this class here. We begin showing that our problem is locally well posed. After that, we are going to prove the global well posedness. So we get u belonging to B. B is in that space that we define here. This is B, C0, 0T, L2, inter L2, 0T, H1. This will be B. So we are going to take u in this class. And so by our first result, we are going to get that this term belongs to this space. And then we have that this problem, now f will be the mu, and mu is this term here. We are going to consider that we have that this problem admits a unique solution, z, belonging to B, and it's given by the following expression. Then from the continued dependence, we have that this holds, and so this application gamma defined by, for each B, we have the solution Z of our problem. We have that this function gamma is well defined. So from the linearity of our problem and having this inequality in mind, we have that this inequality holds also. So on the other hand, if we consider also uv belonging to B, we have this inequality here, and then thanks to Holder inequality, we get this inequality, and using this estimate here, which is true for all w belonging to H1, we obtain from here this expression. From this expression, we get for this expression here. So, in order to conclude that gamma is a contraction when defined in some ball contained in B, we are going to consider a radius capital R, which will be defined later. So, if you take U in that ball that we're going to define later, then we have that this is true. This expression is true. So, now we are going to take capital T0, verifying this quantity here less than 1. And we are going to choose the radius of the ball equal to this expression for all capital T between 0 and capital T0. Then we have this expression here, which proves that our function, that gamma u belongs to the ball. So we have that the gamma takes the ball into the ball for this choice of the radius r. Okay. I'm sorry. And to be a contraction, we have also to have to consider that the capital T have to be between 0 and the minimum of 1 and capital T0, because if you take this, we have that this expression is less than 1. So we have that with this choice of capital T, we prove that gamma is a contraction from the ball into the ball, as I have told before, and using the contraction method, we have that the application gamma has a unique fixed point which proves the local solution. So I have to prove the global solution. As we have that the following energy identity holds, and we use and do some computations, we get that this inequality, and using Gronow's inequality, we have this expression which allows us to extend the solution to the whole half plane. And so we prove the global existence of solution. Now, it remains to prove the exponential decay, as I have told you before. That's our main goal, and that's our contribution, in fact, in that part of this work. And we are going to consider the function lambda essentially bounded, and P can be a number between a number, not exactly a number, but lambda 1 can be a function belonging to LP, and P can be between 1 greater than or be equal to 1 and less than or equal to infinity, okay? And suppose that my function lambda is greater or equal to this lambda 0, where lambda 0 is a positive constant, plus this function lambda 1, which is in LP for almost every x in R. And this is a technical imposition, okay, that we are going to see after. Okay. We are going to ask that the norm of lambda 1 in LP must be less than this constant here, where this constant might be, where CP must satisfy this expression here. So I have to ask this, and so observe, this lambda 0 is greater than 0, but this is not required to be bigger or less than lambda 0, okay? So, for any initial data, U0 belonging to L2, we obtain that the respective Mild solution U of our KdV Burger's equation problem satisfied the decay estimate. We prove this in the L2 norm, and observe that this lambda 0 prime is exactly this expression here. And for this expression to be positive, we have to impose this technical assumption that I told you. That's why we take this, okay? And let's see the proof, which is very, very simple. We see that in order to prove what we want, it's sufficient to prove this expression here. So, from the energy identity, we have this expression. See, with the hypothesis we have on the function lambda, we have this expression here. So, here is the point. So, we do a lot of here. In fact, we have to drop this term here. So we do some computations, and here's the difficult, between aspas, if you think. This is the part, because we have to drop this term. So from here, we obtain the term, which drop this term, and then we obtain what we need. And then we use in Holder's inequality interpolation. We have this term, we work with this term, and then we obtain some computation, and then we obtain the same part of this term we have to drop, but the positive one. And so they drop, and then we have this, and we join with this, and then we obtain what we desire. Okay? And we put the inequalities together, and we obtain the exponential decay we want. And so I thank you very much.
Some questions or comments?